Good evening, everyone. How's been your day today? It's another wonderful time today, and also very awesome one, being the last facilitation for CHM416 for this semester. My name still remains the same, Professor Layinka Jani, your facilitator for this platform. Today, we are going to be looking at the last topic, which is topic 8 for week 8, which is the end of a facilitation. After which we will commend every one of us to the hand of God to help us and to perfect all that concerns us concerning the forthcoming POP exam. So on this note, I say once again, welcome. Today's class will be the end of the facilitation, as I've earlier said, and therein we shall be considering the Module 3, Unit 3, which is the third named organic reactions in the series. So today we are going to be looking specifically at Diels-Alder reaction. At the end of today's class, the learner should be able to, number one, describe vividly Diels-Alder reaction. Two, should be able to show the mechanism involved in this named reaction. Three, you should be able to give examples of dienes and dienophile, which are the two key players in the product formation under Diels-Alder reaction condition. You should be able to present some applications of this reaction in day-to-day synthesis, partial synthesis, total synthesis to arrive at the natural products. All these are part of what should be expecting this class today. Thank you. Introduction. What is Diels-Alder reaction? Diels-Alder reaction is actually one of the most powerful tools for the formation of cyclic molecule. In as much as it's very good for the formation of cyclic molecule, it is restricted to formation of a 6-membered ring cyclic molecule. If you want to synthesize 7-membered rings, 3-membered ring, 4-membered ring, 5-membered ring, then you may have to go through other approach. So we are saying as powerful as this other reaction is, the nature of addition it undergoes is 4+2 cyclo addition, which has to do with 4 carbon atoms from a species, closing up on 2 other carbon atoms on another species. And by that, you will see it will end up forming the 6-membered ring that have strictly one double bond, minimum 1 double bond in the ring. So the position of that double bond in the ring is a position where the formation is enhanced. There are surprisingly few limitations or characters of either fragment. So whatever the nature of your diene is and the nature of your dienophile will help you to know whether you are going to be able to successfully form a new 6-membered ring under the Diels-Alder or not. The number of examples of this reaction that have been studied is very many. And the procedures given here are typical towards that. Although the presence of electron withdrawing group or substituent on the dienophile will enhance the rate of reaction, because dienophile has a double bond, as we'll be looking at it later. So, and at the same time, the carbon that carry that double bond must be put in a position where it's hungry for electron, because your diene is willing to donate pi electron through pi bond outside. So if the diene must be made a very good donor, then your dienophile must be made a very good acceptor before you can easily have that reaction. So if the molecule or substituent around your dienophile are electron withdrawing, they make those 2 carbon-carbon of dienophile to be highly electrophilic, hungry for electron. So it makes the rate of reaction to be very fast, and it makes the product formation to be very easy. So the number of examples of this reaction that have been studied is vast, is very many, and the procedures have been given in topic 1. So the reaction mechanism. This other reaction is a conjugate addition reaction of a conjugated diene to an alkene, which is dienophile, to produce a cyclohexene. The simplest example is a reaction of 1,3-butadiene with ethene to form cyclohexene. And when we are looking at the procedure of this reaction, then we are rest assured so we are talking about diene. Diene must be a conjugated diene. A conjugated diene is one that have double, single, double in that alternating manner. So example, the simplest of diene is what you have here. 1, 2, 3, 4. This is a butene that have a double bond in 1 and another one in position 3. So it's 1,3-butadiene or buta-1,3-diene. That is a diene. And it will require a dienophile. A dienophile is a carbon-carbon double bond. And when this happens, the mechanism of the reaction is in such a way that the pi bond gets out to form sigma bond. If you look at this diene now, he has a pi bond here, he has another pi bond here, the dienophile has a pi bond here. So this made up of 3 pi bonds. But there is going to be relationship in such a way that the first pi bond there is delocalized to this site, while this one will come out to close up between its last carbon and the first carbon of this. Then after done that, for this carbon not to exceed its tetravalent nature, its own pi bond goes out. And it's going out, its last carbon close up on the first carbon. And that's why at the end of the day, you end up to have this cyclohexene. So in this other reaction, you are actually making use of 3 pi bonds in order to produce only 1 pi bond and 2 sigma bond. The first new sigma bond is what you have here that joins that up together. And the second new sigma bond is what you have here that joins this base together. So this other reaction is a reaction wherein 3 pi bond rearranges themselves to end up producing 1 pi bond and 2 sigma bond that end up closing up on 2 carbon atom on the 4 carbon atom to make 6. But the nature of your diene and dienophile is very important. For example, if you are using alkyne as your dienophile, it means that after the delocalization of the pi bond to form a real bond between the two, then the pi bond of that triple bond goes out to form that bond up. You remember here right now you have 3 bonds there, and it's only one of them that you have used right now up. So you end up having a cyclohexene that have an additional double bond. And that's why if this is your normal double bond, position 1, 2, 3, 4. So you now have a cyclohexene that have a double bond on position 1, another double bond on position 4, which makes it to now become diene. So it will be 1,4-cyclohexadiene or cyclohexa-1,4-diene. So the most important thing is that if these dienophiles want to be attacked by the electron rich of diene, then whatsoever that can make them to become electron hungry by attaching electron withdrawing group to them, we increase their rate of acceptance of the bond from the diene and therefore make that reaction to be very fast. So if you are looking at this ordinarily, that you are reacting ethene with butadiene, if the reaction is taking 20 minutes, for example, to form, If you now put a nitro group on position 1, which is an electron withdrawing group, it will take less than 20 minutes to form. Why? Because the electron withdrawing group that is attached to your dienophile has made your dienophile to be much more hungrier to accept readily, easily, and with a very fast rate the donation that is coming from your diene. Therefore, if your alkene here that is non-substituted is taking 20 minutes to form your cyclohexene, by the time you put a nitro group here, it may not take more than 5 minutes. If you put a nitro group up and down, there is a cumulative electron withdrawing group. It may not take more than 2 minutes. So that's why we are saying the nature of what you have on your dienophile can increase the kinetics of your work and make your product to be formed on time. So whatever it is, just know how to move your bond. A diene and a dienophile, anytime, any day, what will happen is that this one form a double bond at the vertical, and double bond here comes out to close up this place. And when that happens, the double bond here also goes out to close up this place. So what will you have at the end of the day? 4 + 2 cycloaddition, where you now have specifically a double bond in that position. The beauty of this movement, knowing how to move this arrow, is that even if they give you the final product, you can from there walk back by what we call read through those other reactions to know what are the starting material that forms that product. Like for example, let's assume we don't know what is here. They just told us that, oh, something diene react another thing dienophile, and they form this adduct. What you form as product of this other are called adduct. If they say this is the adduct that was formed, and they are asking you, what will be the diene and the dienophile starting material you will need or require to get this cyclohexene done? So you can reverse the way you move arrow, and you will see the two starting material will show their face. But how do you move? You move in such a way that first check your adduct. Is it this other adduct? If it is, 1, it will be a 6-membered ring. 2, it must have a minimum of 1 double bond in a vertical section. So when we look at cyclohexene, it's a 6-membered ring. 4 + 2 cycloaddition, 1. Then it has a double bond vertically inserted in the ring. So it's this other product. So what are the starting material that form this product? You will start from that same double bond and begin to move. If this double bond comes to this place, to make this place double bond, in order for this carbon not to exhibit tetravalent nature, then this next bond here will break and go and form on this place. And for this carbon also not to be tetravalent, more than tetravalent in nature, but this new bond that has come in, this will break and come here. And when you look at that product very well, you can know what has happened. Here that is 1 bond before. Here that has a bond before, it's already broken. There is no bond here again. So when you have this before, by what we have done right now, there is nothing here again. So there is nothing in this side again because that bond is broken. So you have here, but there's nothing in the other side here again. So when this one comes here, that forms a double bond now because another one has come to join it. This becomes a double bond. The double bond that is vertically placed here before, that pi bond has been used, so it remains, this vertical becomes single bond. And then the next place to it that is single before, the pi bond has been moved there to form a double bond. And there's a breakage here. So that's the first product. You can see that's your diene. Then when you come here, you have already broken this place. You have already broken this place. What you now have left is this vertical one, which was 1 bond before, but because of this one that has come to join it, it has become 2. So if you look at this now, What you have done to walk back to know your starting material is called the retro disorder approach. So with this retro disorder approach, we know that, oh, cyclohexane must have been formed from a butadiene and ethene. And see it when I remove it, exactly that is what we have. Exactly that is what we have. So if it is second one now that is having the issue that we are saying, oh, okay, you cannot do anything to that, or you say you don't know what the product, what the starting material will be, but they gave you the product that this product is formed. What are the starting material that will help you to form this product? You just come again, it's a 6-membered ring. It has a double bond within, so it's a disorder product. So the double bond here come here. And by virtue of that, this bond will break to go directly to the next phase. And by virtue of that, this bond will break to go to the next. So when we look at that now, we see that this new system is starting from here because this one has been broken away. So we said it's starting from here. It moves like this. It moves like this. So it breaks away here. But here now, single bond before, by the movement of that bond that broke into this place, it becomes double bond. This one is double bond before. By the virtue of its movement, it becomes single bond. This one is single bond before. By the virtue of the bond that comes to him, becomes double bond. So that's the first starting material. The second starting material is that you know this place is already broken. You know this place is already broken, so you have only 2 carbon atoms left here. One up and one down. That initially has a double bond. And by the virtue of the broken that has come into it, it now ends up being a triple bond. So you can see, oh, the 2 starting material that can lead to this other product will be butadiene and alkyne. So these are how to go about understanding and identifying what is a product of 2 diene and dienophile coming together to form. What is the adduct they will form? And if you are given the opportunity to know the adduct, then you can say what are the starting material, diene and dienophile that forms them. So let's now say, since we know that in the mechanism study, majorly the success of this other reaction is depending on these 2 key players, the dienes and the dienophile. Reaction is usually thermodynamically favored due to conversion of 2 pi bond into 2 new stronger sigma bond. I hope you know that because we said it, that you have 2 pi bond in your diene when they move, and you have 1 double bond in your dienophile. By the time they move, the product will have only 1 pi bond, and 2 sigma bond will have closed up to form the 6-membered ring. And that's why we are saying 2 double bond or 2 pi bond end up being used to form 2 sigma bond. And that sigma bond, you know, is stronger than pi bond. And what we are saying here is that here now you have 2 pi bonds, but here now you have added a new sigma bond that closed up that face, a new sigma bond that closed up this face. So if you have looked at the whole of the 2 before, they are made up of 3 pi bond. But if you look at the product now, you have only 1 pi bond. That means 2 pi bond has disappeared. If you look at the starting material before, there is no sigma bond that link the 2 carbon atom to 4 carbon up here. There is no sigma that link the 2 carbon atom and the 4 carbon atom downstairs here. But in this place now, you now have those 2. And you know sigma bond is always stronger than pi bond by reason of the overlap that forms them. So that's the reason why it is a thermodynamically favored product. So the 2 reactions shown above required the harsh reaction condition. But the normal disorder reaction is favored by electron withdrawing group on the electrophilic dienophile. That's what we are saying. Dienophile is electrophilic, is hungry for electron. So if it has substituent that are electron withdrawing on him, they will have sapped away electron density from him, making him to to be seriously hungry. So when somebody that a dienophile that needs to collect is already seriously hungry, then when the donator or donor is coming, it will be easy to quickly give it to him. That's why we said, if you don't want the reaction concentration to be too harsh before you can achieve your aim, selectively choose your dienophile right. And what makes your dienophile to enhance the kinetics of the reaction to be very fast is to make that dienophile to be electron withdrawing centered, or to have electron withdrawing substituent around it. That's about the dienophile. But when we are talking about the diene wants to donate. So anything that pump electron into him, like electron donor, we make him to be very, very available to donate to the dienophile, and therefore we enhance the reaction. And that leads us to a typical example of diene and the dienophile. Some of them are aliphatic diene, some of them are cyclic diene, some of them are aliphatic dienophile, some of them are aromatic or cyclic dienophile. So let's look at diene first. Anytime you have carbon double bond that are two in conjugation, where they are conjugated is where the diene will answer to you. So example of such is what you have here. See, this first one is buta-1,3 diene. If you come to this second one, even though they have a methyl substituent here, CH3, but you still have your two double bond that are in conjugative manner, is a dienophile, is a diene. And this diene may be far, far better donor than the first one, because there's an alkyl group of CH3, which is donating or pumping electron density into the site, making it to be richly available for external donation. Example of cyclic diene is what we have in this third one. You can see that this is cyclohexene, but with double bond of position 1 and 3. This is cyclohexane 1,3 That's going to be a good diene, because you can see there are two double bonds, and those two double bonds are in conjugative manner. If the double bond has been like this, even though this one is cyclohexadiene, it is not a diene that is needed in this aldehyde reaction. Why? Because these two double bonds are not in conjugation. Look at where they are. It's double bond. Next to it is the single bond. Next to it is the single bond. Next to it is now the double bond. They are broken their rank. Anytime you have conjugation, it's a double, single, double, single, double, single. If I have this one, double bond, single bond, double bond, single bond, double bond, single bond, this is what is called a conjugative system. It's conjugative as far as these are in alternating manner. But when you come to the last three carbon I draw here right now, it's no longer in conjugation with others. This is double, single, double, single, double, single, double. To that place is conjugated. But if you come to the next one, single phase, next to it again, single phase, before you now come to the double phase. So this is not part of the conjugation. So if I give you another compound, and see whether this one can be a good diene, despite the fact that it has two double bonds that you can call it diene, but is it a kind of diene that will work in this other reaction? This is a diene, but that diene double bonds, those two double bonds are not in conjugation to each other. See, double, single, single, before you now get to double. So when you say something is a diene, it doesn't mean that it can actually be a useful diene for this other. A compound that have two double bonds are called diene, but those that have those two double bonds in conjugative manner are the only one that can successfully work as a starting material diene for this other reaction. So we look at this, for example, if you look at that down one, those down one are the examples of the dienophile. I want us to look at it. This is the dienophile because we are zooming in on this C double bond C here. is a dienophile. But this dienophile compared to ethene as dienophile, which one of them will be much more reactive? This one. Why? Because in ethene, what you have attached to it is hydrogen, which is not donating, which is not withdrawing. But in this one right now, you have a COCH3 attached to it, which is an acetal group. And you remember that any C-double bond hole of sp2 hybridization of aldehyde or ketone are electron withdrawing in nature. So this whole thing here now can be referred to as electron withdrawing group attached on our dienophile. So the rate of forming adduct with this will be far, far faster than with this. So these are what some of the example of things we should have understanding. So when you call something a dienophile, it's only interested to zoom in on the C-double bond C. This one will be far, far faster than this first one, because cyano group is more electron withdrawing than the carbonyl group. It's another one here, dienophile, that have two extra groups on position 1 and 2. That will be cumulative electron withdrawing potential on that and make it to be enhanced. You see this one, parabenzoquinone. Parabenzoquinone is a good dienophile. Why? Because this is the C-double bond C of your dienophile. Next to it is a carbonyl up. Next to it is a carbonyl down. So it means that two electron withdrawing group up to him and down to him. And then another beauty of this benzoquinone is that it has two faces it can use to be a dienophile, which means that with that kind of a thing, you may be able to successfully form polycyclic compound. Let's say what I'm trying to say is this. It's a very good and useful tool to get plenty group polycyclic compound. Let's say, with this dienophile part, we react it with this diene. And with the other dienophile part, C-double bond C here, you react it with another diene. Let's see what happens there. When this one moves down, this one goes out to close up that part. And this one goes up to close up this part. So you see at the end of the day, for this one side now, that is like this, having the benzoquinone here, you must know how to move that electron or those bonds. Is very important for you to know how to close up. So you have this now. From this movement here now, this becomes single, this becomes double, this becomes single, and pi bond that comes out of it join here. This was double before, it becomes single because pi bond that comes out of him close up this place. With that one phase, you have been able to form a new cis-membered ring. Then for the second one too, move your bond here and move the bond out. The out one will join here and the out one will join up. So when you have that, the second diene is this. So this middle becomes double bond. This becomes single bond. The bond that comes out of here joins here. This bond here that comes out of here join here. So you see at the end of the day, you have a tricyclic compound by virtue of those two faces of dienophile. So these are all examples of diene and dienophile that are the key player. Stereoselectivity. This other reaction is very stereospecific with respect to both diene and dienophile. And what do we mean by this? It means that you remember that your diene and your dienophile have double bond carbon-carbon, which is an sp2. And you know the molecular geometry of sp2 is planar. And that means around the double bonded carbon-carbon, you can have a particular orientation of either cis or trans. So we are saying that this other reaction is stereoselective in nature, depending on what is the stereochemistry of your diene and your dienophile. For example, if you are using a dienophile that is having an alkene that have a cis isomer, a cis isomer of an alkene means that the two bulky group that are linked to that carbon-carbon double bond are on the same side of the plane. When you are treating that with a diene, it will end up giving you a this either adduct that will have a cis substitution around that ring system. However, if your dienophile is arranged in such a way that the substituent attached to that carbon-carbon double bond are in trans form, when it's closing up on your diene, you end up getting a trans isomer of your cis membered ring. Looking at it, for example, let's take that of dienophile as an example. You see, this is your dienophile here, this double bond here. And you know that to this side, there's an hydrogen. To this side, there's an hydrogen. We may not need to write it, but you already know. But you see, the bulky part of the group linked to this carbon, there are two groups linked to this carbon, hydrogen to the right, or to the left, and methyl ester to the right. The two of them is this, but the bulky group is the methyl ester. So if you come to that second carbon that is playing roles in that double bond, its bulky group is to this side. So the two bulky groups are on the same side of the plane here. So it's a cis dienophile. When this one reacts with your diene, form a new cis membered ring by that, which is this one. But because you know that these carboxylate group are on the same side of the plane, the adduct you are going to form as a product will be shown that is in the same side of the plane. You see, it's as if you have added carboxylate ester group to the same side of the face of this compound. It's a syn addition. You remember the syn and the anti-addition. If you have a double bond, and then you are adding two heteroatom to it to form a single bond. Maybe A is added here, B is added here to form an alkene. So we said that one is cis addition. It's a syn addition. But if to get your double bond to single bond, A is added to the first atom up, B is added to the second atom down. It will still form your single bond, but with the substituent being on different side of the plane. That will be called the trans. So when you look at that, wedge and dash convention is what we normally use. If you are using wedge line for both up and down, you are saying they are in the same side of the plane and they are having like a cis syn addition. But if you use wedge for one and use dash for the other, you are saying one is going to the plane of that system, one is coming out, so it's like a trans one. So when you look at the dienophile here, we discover that the dienophile up is a cis alkene, so we end up giving us a cis product. And if you look at the second one here, the dienophile is here. The bulky group here on the up is to the right. The bulky group to the carbon double bond there to the left or to the down is to the left. And that shows that this diene, this dienophile is a trans one. By the time it's closing up on your diene, you must make sure that the stereochemistry is the one in which it is a trans one. So that's what we are trying to say. So a cis dienophile will give a cis product of adduct, while a trans dienophile will end up producing a trans this other product. Stereoselectivity continues. If the diene, let's look at diene being the one that is having that stereoselectivity. It can also have its own effect. If the diene substituent has the same stereochemistry, in the illustration that follows, they are both E isomer. If the diene substituent have opposite stereochemistry as the one you have, it's called the Z isomer. And you know, when we are talking about E and Z, by now I'm sure that you are not supposed to be confused. Because when you are talking about E isomer, it's just like an abridged version of trans isomer. If you are talking about the Z isomer, it's just like an abridged version of the cis isomer. Why? Because in the cis and trans, the substituent on your double bonded carbon are the same. But in Z and E isomer, those substituents, one is bulkier than the other, but yet you can still recognize that those two bulky groups, though not being the same, they're on the same side of the plane, is Z isomer. Oh, those two substituent attack, they are the bulky two group, but they are not being the same, but they're on the other side of the plane. It's called E isomer, which is your trans isomer. So looking at the diene in the context of what we are talking, we discover here that, for example, looking at this compound now, you see your methyl group is on this carbon. Another methyl group is on this carbon. So if you want to look at this carbon as a long chain, it's going to be 1, 2, 3, 4, 5, 6. So that is X diene. One of the in is on 2, one of the in is on 4. So this is hexa-2,4 diene. Now, when you look at that, being treated on a dienophile that does not have any stereoselectivity because it's a triple bond that is there, which is an sp hybridization with bond angle of 180 degrees. So you discover that what will determine your stereochemistry is around that your diene in this form. And when you look at that, you need to zoom in on them one by one. You know, this place will be hydrogen. This place will be hydrogen. So if you first of all zoom in on this first double bond part, you discover that across this carbon-carbon double bond, it has a bulky group here, which is a carbon, and a tiny group here, hydrogen. This one has a bulky group up, which is a methyl, and a tiny group down here, which is hydrogen. So when you look at this very well, you discover that the two bulky group, though not being the same, but you can track them. The bulky group around that first carbon here is the CH3. The bulky group around this second carbon here is the C that extended down. It's not just ordinary CH3, but it's the bulky group. And when you look at that, you discover that, oh, the two bulky group are not on the same side of the plane. Because for this double bond, this is one side of that plane and the other one. So you see the bulky group here is up, but the bulky group here is down. They are not like here and here. So this is like an example of a trans isomer. But because that trans isomer now, the two bulky group that you are using to know the position of their double bond, the plane where they belong, are not the same thing. So instead of calling this one a trans, then you call it E isomer. And that's the reason why when you are trying to attach that, you look at this one also separately as the second double bond. You have to look at this second double bond separately on its own. You discover that, oh, you have an hydrogen here. You have the hydrogen here to complete. So the bulky group on this carbon is on the upper plane, while the bulky group on this carbon is on the lower plane. They are not in the same plane. Why this one is above the plane of the double bond, this one is below the plane of the double bond. But this one is CH3, but this one is not CH3. This one is CH. So the two bulky group are not the same thing. So instead of calling them, even though they are on the other side of the plane, instead of calling them trans, then it will be E. So this kind of hexa-2,4 diene is a kind of the one we can say E, comma, E, hexa-2,4 diene. Hexa-2,4 diene. So when that is treated with the dienophile, you can see the stereochemistry of the product afterward, which means the stereoselectivity of the chemical nature of your diene here is one that played a significant role in the kind of the product we have. So stereoselectivity can also appear or can also be noted in cyclic diene. Cyclic diene can give stereoisomer product depending on whether the dienophile lies under or away from the diene in the transition state. And when this happens, it can lead to a endo or a exo product. The endo product is usually the major product because it's a product that gives room for a lower energy state and a higher thermal stability. And it's highly kinetically controlled product because it has the easiest way to be formed because there is no restriction, there is no repulsion, there is no interaction that is affecting their formation. And when we say that, we are saying that it is endo. When it's a compound endo, it is endo if the base of the crown that is attaching to your diene is tilting away from the plane of what that diene has formed with dienophile. So it has a lot of space between them that allow for stability. But if you are saying an exo, it means the head of the other dienophile that look like the crown is tilted upward towards the head of the new thing that was formed between the diene and dienophile. And therefore, there is a small distance between the head of this and the head of this. So it's not going to be as stable as this one where his crown is far, far down below and it's not having too much interferences with the newborn that was formed. But however, we may need to also look at how is this thing formed so that we are not confused. How can this thing form, even though it can lead to any of the two products, but how is it formed? You remember that we said the diene must initiate. Double bond comes here, this double bond goes out. And the one that goes out is what closes these two places. And when that happens, you discover that the middleman we want to have challenge. This place now, on close proximity, we have to be arranged in such a way that is minimizing repulsion away from this. So what happens is that this is 1, 2, 3, 4, 5. That carbon 5 is lifted up. These two we bend like this to link to 1 and 4. Remember, this is 4. This is now your 1. This is your 4. Then this is AB that it wants to close up with. So it comes around with AB that it wants to close A and B wants to close with. And when it does that, this is what happens. So the two here are what you have here. The 4 here are what you have here. So where is carbon number 5 here? Is tilted away to get a better stability. Is the one that now link between 1 and 4. Remember, this is 1, this is 2, this is 3, this is 4. This is 1 and 4. So there will be a new double bond between position 2 and 3. There's new double bond between position 2 and 3. And there's a new bond sigma that is formed between the position 4 and then the base B of your dienophile. And there's a new double bond that will be formed between your A head and the up of your 1. So this is your A head and this is the up of 1. But between 1 and 4, there is a methyl group that is linking them together before, which we are now saying this is bridgehead 4, this is bridgehead 1. The two of them close up at that end. This is the carbon, this carbon that we call 5. So you have been able to do it, the joining to this level. So what now happened to the crown head here? The crown head here, we said it could bend downward, far away. You have double bond, oxygen, oxygen, you have your double bond here, you have your double bond here. When you have that, it's called endo product. You can see how it tilted its head downward. That is an endo product. But it is also possible that you can have an exo product. An exo product will tilt its head up. Its head will be up, having that 3 system with the carbonite and 1 and 3 position. You can see the head you have here is up. The head of the crown of this guy that is linking to them is also up. So that is exo products. So we have a lot of things like that. It will take a lot of time of practices. Then you see that all these things are not difficult. Synthetic applications of this other in cortisone steroids. You know, steroids are they have 4-ring system. The 3 of those ring system are 6-member ring, and the last is a 5-member ring. It is very useful in the synthetic application of getting this steroid synthesized. All what you need to do is just to have a dienophile of suitable orientation. Then it will undergo some other reaction transformation to get to where you are going. So one of the synthetic application of this other reaction is in the synthesis of steroids. So one of the earliest and the most important example of this other reaction is the total synthesis, which actually is useful in the synthesis of steroid cortisone and cholesterol. Cholesterol also have that steroid ring. But one thing you must have at the back of your mind is that when we are talking about total synthesis, you are trying to get a natural product synthesized, starting with laboratory reagents. So if you look at this here, you can see this is your diene. And if that is a diene, for our suitability, we discover that this is a dienophile. You remember parabenzoquinone. So when this one closes up on this side, there will be formation of a new 6-membered ring. This carbon is now here. This carbon is now here. This single bond has now become double bond by the virtue of what? Moving this one here, moving this one out. This one that you move out is what joined this side. And this double bond you move out here is what joined this side. So you are going to be having this as this. Then the new 6-membered ring is what you now have here. You can see that there's a methyl group on this guy before, which is now up. So having said that, then you form this second product. Like I say, there's different way of getting natural product. You can have total synthesis, you can have partial synthesis. Partial synthesis have to do with you start with another natural product of smaller molecular origin, and you now try to use your synthetic skill to build up other things on it to get to a higher naturally occurring compound. But then we are saying total synthesis. You are starting totally from a simple laboratory chemical to get to that final product. You see that cholesterol is in human system, is the counterpart of what we have in the plant kingdom when we are talking about terpenoids in plant world. Then we'll be talking about the steroid in the human and animal world. A majority of hormones in the human body, majority of them are this steroid-like in nature. The only thing that is different are the substituents that are added to them. You're talking about testosterone, sex attractant hormone, and all those things. The majority of them, they are all steroids. Estradiol, cholesterol self also have the same ring system of steroid. Lanosterol. All those things are very important to life, and you can also get them synthesized by your knowledge of this other. So the second stage here, you react it with aqueous sodium hydroxide to put a basified environment there in dioxane, after which you neutralize that environment after he has achieved his aim by adding aqueous HCl. And afterward, the transformation with other reaction leads to this steroid cortisone. Another synthetic application of this other reaction is in preparation of various drugs. Example of it is tetracycline. You know, tetracycline, we all know the structure, we all know tetracycline, how it's a very valuable antibiotics that has helped man over the years. But you know, the beauty of it, tetracycline has structure. This is the structure of tetracycline. And here you can see the essence of diene and dienophile coming up to close up these two bulky molecules in order to have the intermediates that can easily be transformed to the final tetracycline product. Remember, if you look at this intermediate that was formed, is having 5-ring system, but your tetracycline is having 4. What happened is the hydrolysis that led to the breaking of this ring. There is ring opening reaction that happens here that turns these ones to OH and turns this one to NH2 of amide. This is where you have this. Is that 5-membered ring that open up to form that. That's why tetracycline has 4-ring system, 1, 2, 3, 4. But the intermediate that was formed by this other reaction at 85 degrees centigrade for 48 hours is having 1, 2, 3, 4, 5. So the last one here opens up, then you get tetracycline. Last activity. Define desired reaction. There's no problem with that anymore. Using desired, show total synthesis of steroid cortisone. That's what we just finished. Complete the reaction below. Complete the reaction below. It's not difficult to do that. All you need to do is come to where your diene is, move it, and let your dienophile move up. The product of this reaction will just be every other thing that are not part of it. Repeat them the way they are. Don't let any molecule intimidate you. Just know the principle. Here you have this, here you have this, and here you have a 3 bond. But this 3 bond, one of it is going out. So it remains 2 bond. 2 bond bonded with cyanide up. 2 bond bonded with cyanide down. And when this one closes up, this single bond becomes double bond. And when the double bond here is going out, it comes to link as a sigma bond here. When the third bond of this triple bond goes out, it goes and link up here as a sigma bond. So at the end of the day, that will be the product of that reaction. Then the second one here is not difficult. You say here you move and this one goes out. And when that happens, this one goes up to go and close up. So you can tilt this one to a side. And then it's coming here to link up. So there's something in carbon 1 and 4, which is an oxygen, which link up at 1 and 4 position. And the 3 crown head of your compound here tilts downward to form the endo product. I told you endo product is standardically favored. Remember, this one now becomes double bond. So this one will be the product of these two reactions. On this note, we have come to the end of the facilitation for this session. If anybody has any question, please make sure you watch all the video. All the recorded video are facilitation session in brackets recorded. If you go to the course page of this class, you will see all of them under their link and then watch them again and again. And if you have any question before the exam, you can reach me through my email, or you can have time of chatting with me. So we have been able to, number one, describe the desired reaction. Number two, we have been able to show the mechanism involved in the reaction. We have been able to give example of diene and dienovice, and we have been able to present some synthetic applications of this compound called desired product. On this note, we have come to the end of the facilitation for this semester. Thank you very much, and God bless you.